Hello, welcome. We'll start in just a couple of minutes just to see if a few more people show up. But thanks for joining us. We'll see you soon. Okay, then. Good afternoon, everyone. Thank you for joining us all the way to the bitter end. And this basically does mark the end. This At the end of this lecture, we would have covered all the material that you're responsible for the final exam. And thank you for sticking with us through all this somewhat challenging and crazy times. But here we are. There is a couple more topics that I actually like to cover. Um, One being Maxwell's equation and the EM wave, which is what the whole course is building towards. And then for those of you who are going to electrical engineering or computer engineering, the discussion on AC circuits is somewhat important. So I kind of like to cover that. It won't be covered on the final. You won't be tested on it, but I like to kind of host a couple more live stream sometime towards the end of the exam period. I'm thinking like April 20th, April 21st or something. I'll make an announcement about that. But maybe you can indicate in the chat if you would be interested in such thing and you join us for that. Or in any case, I'll probably still do it and you can watch it anytime during your break or whenever you feel like you want to. But back to today. We're going to talk about inductors and transformers. Two fairly. Inductors is just a kind of carryover from what we did last week, and transformer is kind of tossed in there just because it's so dead easy to work with. So we often just stick it in for completeness, I guess. But it's a very useful device, and you see it kind of everywhere. Let's get the show on. Inductors. So inductors kind of is what happens when you put a coil in a circuit, right? We've kind of taken for granted that somehow we have this coil in space and that somehow there's current going through it. But in order to supply current, you have to include it in a circuit. So how does it actually behave as part of an overall circuit? Well, if you have a voltage like this, then you're going to have some current, which kind of comes in here and goes around the loop like that. As a result of this current, you're going to create some magnetic field, right-hand rule. We get that the magnetic field goes that way, which depends on the current. But then here's the funny thing. When you first turn it on, right, you have a huge change in the voltage, right? So then you got some kind of dV/dt, which as a result will give you some kind of change in the current, right? So then this guy will have some kind of change in the magnetic field, and now you have a changing magnetic field inside a loop, which is going to give you a change in magnetic flux. You can use subscript M or B for magnetic flux, which then by Faraday's law then you're going to induce some EMF, in the coil, which would then affect the voltage across the coil. And because of Lenz's law, you know that this is going to oppose the initial change. And that's why we call this kind of phenomenon self-inductance, right? It's creating a changing magnetic field which then induces a EMF on itself. Your textbook also goes through this other thing called mutual inductance, which involves two separate circuits, but we're not going to get into that in very much detail. We're going to focus on self-inductance, or in most cases, inductance, that we're just referring to. And this doesn't actually violate what we said earlier about no self-force, right? Because it's all the other parts of the wire that's affecting any other part of the wire. It's not the wire. Each segment of the wire doesn't affect itself, but the whole thing, all the other parts of the coil is affecting each other part of the coil, sort of thing. So then, how does this all come together in terms of the numbers? Actually, before we hit the numbers, I want to show you this one video, right? Because ultimately what this does then is you're opposing changes in the V, which technically you're more opposing the changes in the currents, which relates to the magnetic field, right? The magnetic Faraday's law aims to resist changes in the magnetic flux. Changes in the magnetic field relates to changes in the current. So the solenoid opposes changes in current. And so you can watch this video. That the link is in the description of the video below, but I'm just going to show you the highlight there. Let me turn the sound on here. So this is by Physics Girl. She does all kinds of good work, and what they have here is a demonstration where they use this big giant coil to create a giant magnetic field inside to demonstrate something. But this coil also acts like an inductor. So how does this inductor play in this particular circuit?
Because of the magnetic fields produced by the currents that push them apart, but learning. Now when we turn off the current, things get real saucy. Okay, that jumped off, and then,
Boom!
Oh my gosh!
Right? That's the spark from turning off the current. Stealing her words there. It's because at the moment you flick off the switch, right, you change the current from something to nothing. So you have a huge decrease like that. Bam. Basically a vertical decrease. So this di dt is reaching technically negative infinity, but huge, right? So you're going to basically get as much EMF or V as you need, sort of thing. As a result, the space between the two contacts of the switch develop such a huge voltage between them that you're moving past the dielectric breakdown of the air, producing that spark. So think of it this way then. Self-inductance as a thing. The idea is that if you have a change in your current, right, in the coil, then you have a change in your magnetic field, which then gives you a change in the magnetic flux within the coil. And by Faraday's law, that means you can induce some EMF around the coil, which is basically a voltage, which then in turn changes the current within that circuit. So what the coil is basically doing is, because it's got some energy stored up in the magnetic field built up within the inductor, it's able to resist changes in current by providing the potential or the voltage or the EMF necessary to keep on supplying that current, to resist the change in the current. So let's work this out with Faraday's law then. I'll give you a more formal process to do all this, but just a way to introduce the concept of inductance. So let's just call this V because it's a circuit, right? So technically EMF is the change in potential or the difference in potential between 2 points. This is just, we're just talking about voltage. And that's a magnetic flux. And if you consider a single link in the coil, right, like that, if you look at it head on, say the current goes this way, then by the right hand rule, you know that the magnetic field is going to be, I guess in this case, out of the page, but the key thing is that the magnetic field is perpendicular to the area at every single point, which means it's parallel to my dA vector, which is normal to my area. And we already talked about inside a solenoid. Oh yeah, this is for a long, straight solenoid. And we stick to this because by Ampere's law, we can show that the magnetic field inside the magnetic field is uniform. So in that sense, this is very much like the parallel plate case for the capacitor. This is kind of like the simplest math you can do with an inductor. So that's why often we do a long straight solenoid. Given this niceness, this flux term just becomes B times A, which is, and then B we know is mu naught n times I times A. So we can sub that in. So V is equal to negative big N d dt of that, which is our flux. Now, for a given solenoid that's not changing shape, right? The area is going to be the same. The loop density is going to be the same, right? So all those can come, they don't change in time. So all those can come out of your derivative. So what you're left with is just the possible change in current that you might have to work against. And actually I replace this with N over L, L for the length of the solenoid. Like that. And now we have an expression that relates two things we often measure in circuits, right? Voltage and current. And everything else, there's this big chunk in the middle that looks kind of messy, but that's not expected to change in time. It's given for a given shape, size of coil. So very much similar to what we did to capacitor, we just kind of put a big box around it, and we call this thing inductance. And we're going to use a symbol L to denote inductance, because I guess we can't use I, it looks too much like a 1. And the unit is measured in H henries. So what we have is a governing equation for the inductor can then be written as such. This particular expression over here happens to be how you would calculate the inductance of a long straight coil given the geometry of a long straight coil. Just gonna, at the risk of overloading this slide here, you can also have an alternate form where we use the loop density instead. So we put the L on top as a result. So that's an alternate form. So they're both equivalent. So how does this actually physically look like, these inductors? They basically look like a coil in most cases, as you would imagine. But of course, we usually have some kind of an iron core inside just to amplify the magnetic effects, just like how we did with electromagnets. And at this point, a number of people on their muddiest point ask me about how does inductance relate to capacitance, because they feel like they're sort of doing the same thing, but not really. And in fact, they are really two sides of the same coin. So there's some clear similarity, but some very important differences. Let's talk about the capacitance for a second. So capacitance, quick review here. A capacitor builds up a charge, Q. Right? Here's a capacitor, builds up a charge. As a result, you get some electric field inside such the vicinity inside. And that electric field stores up energy in the electric field. Given the electric field, then you can talk about the potential difference between the two plates. And then the actual governing equation is Q over C. On the other side, the inductance builds up a current inside a loop. And then as a result, stores energy in magnetic field instead. We talked about last slide that we would use Faraday's law to find that your EMF is equal to negative N d magnetic flux over time, right? Which then leads to the expression of that. In the sense, this one resists changes in current. Whereas actually back in the capacitor side, if you think about it, because the charge stored up in the capacitor takes time to get rid of, right? In a very similar sense, the capacitance actually resists changes in voltage because it resists changes in the charge. It takes time to move the charge around. And one more thing to distinguish between these two things is recall that I is equal to dq dt. So this is actually the time integral of the current. So the capacitor works based on the time integral of the current, whereas the inductance works with the time derivative of the current. So you can see they're really very similar, two sides of the same coin. They both store energy, yes, but more often we think of capacitor as a storage of energy because we're more used to dealing with having a certain potential or certain voltage, whereas than having a source with a certain current. So in most cases, the application of inductors, it's not so much for energy storage, but rather it's really based on this particular form, which is different from the one for capacitor, and giving us certain various filtering kind of aspects. So from that, you can kind of also see a very parallel process of developing what and then how much inductance there is for a given shape, size of coil. Very similar to the capacitance case. Let's quick review. So capacitance, we have two conductors, right, of some geometry, and so we always, the first step is to assume that the capacitor one of the capacitor has Q plus Q, the other one has minus Q. Based on that, we find the electric field at all points, so that you can find the potential difference by taking this integral. And then once we have that integral, the C is equal to Q over delta V. Right, that's how we find capacitance. So on a very parallel basis, we can find inductance by doing this. For a given coil, given geometry, we find and assume a certain current that's going through. And hopefully it cancels out the end just like the Q. And based on this I, we can find my magnetic field. Knowing that magnetic field, we can find the expression for my magnetic flux, which is the integral of B dot dA. And there's various things that can simplify this flux integral. And then we use Faraday's law. And take the time derivative of whatever expression we have left from over there. Then, because we know V is equal to negative L di dt, so we can flip this around and say L is equal to whatever V you got divided by di dt. And this V is, we're going to use from step 3. Negative, of course. And hopefully here, any I you have left cancels out. And so that's one type of problem you'll see for inductance, where I give you a certain shape with certain dimensions given. Then you can work out what is the inductance of that particular shape. That's one type of question you'll see. Very similar to the capacitance question, right? And I already kind of did most of that process with this case here, right? We assume an I right here. And then we worked out the expression for B, which is right here. Took the time derivative, which is right here. And then basically divided by negative di dt and see what's left. But if you really want me to go through step by step again for this long straight solenoid case, please let me know by the chat, and at the end I can totally do that for you guys. But that's one type of questions. Same with capacitance. We'll have other questions involving circuits, right? While there is ways to kind of combine inductance in series and parallel, in fact, it's exactly identical to resistance, you won't often get a circuit of pure inductance, just because even the winding of the wires within the inductor represents some non-zero resistance. So we're going to be again dealing with circuits with a combination of resistance and inductance, and no surprise, we're going to call those RL circuits. And similar to when we dealt with RC circuits, we'll have a set of problems that solely focus on these extreme cases when it's fully discharged, fully charged, immediately after we flip the switch, after a long time, all those keywords. That's going to apply here as well. The wording is a little different because we're not dealing with charges with an inductor. So we use the word energized. So fully energized. Or fully de-energized. And the tactics is basically the same. We're going to go in and replace our inductor with certain simpler components at that particular time, and then get rid of all of them so that we'll just have a simple resistor circuit. We can do our Kirchhoff's rule easily on such things. So record a governing equation of my inductor is negative L di dt. So then an inductor does this thing by trying to keep the current the same before you do any change to it. So if we look at the case of energizing, or quote unquote charging for the parallel to capacitor, we're going to start with a fully de-energized thing, and then immediately after connecting some kind of switch or whatever, what's going to happen is the inductor will try to preserve what it had before. So before it got connected, the I was 0. So afterwards, immediately afterwards, it tries to keep I to be 0. And in fact, then you're like, oh, well, can it do that? Can it completely make sure that the current is 0? Well, for the most part, it sort of can, because if you have a very abrupt switch, right, you have some voltage over time, there's no voltage, and bam, suddenly there's voltage, right? This is again it's basically a vertical thing, so your di dt is infinite, which is giving you as big and give you an EMF as big as needed to keep I equals 0, at least temporarily. And when your current of a device is 0, we replace that with an open switch, right? Much like a fully charged capacitor. No current, replaced with an open switch. Now, if it's after a long time, long time later, this implies some kind of equilibrium has been reached. then the current is going to be stable, meaning di dt will be 0. Therefore, meaning the potential or the voltage across your inductor, V sub L, is also equal to 0. If you have a circuit component with no potential drop, we're going to replace that with a simple wire, which is pretty much exactly the case for a fully discharged capacitor. So you can see how these things are, the inductor really looks like the flip side of a capacitor in many, many sense. Then if you're de-energizing or quote unquote discharging, then immediately after you disconnect, you're going to get this big downward jump, right? Which again gets you a huge didt, right? So you're going to try to keep the same current as before you flip the switch. And again, it can do that because you can provide as much EMF or voltage as needed. Because once again, the didt is approaching infinity. So very similar to how we would have done with RC circuits, we would go in and replace all the inductors with wires or switches and analyze it that way. But if we're talking about the any time in between, just like the RC circuit, we're only going to stick with the simplest of cases. Where we only have one inductor in series with one resistor having a current sort of like that. And this, by the way, is the schematic symbol for inductor. It's not the sharp jagged lines like the resistor. It's a bunch of humps, smooth round humps that looks like, I guess, the loop, but they didn't want to draw circles. Darker green happening here. So if we do the loop rule of this, you get plus V through the battery minus L di dt minus I times R through the resistor gives you 0. That's the loop rule. And so, you once again have a first order differential equation that's linear. So you want some solution of the form where if you take the derivative, it looks like itself. That again is your e to the t sort of form. And to know which kind of thing you end up with, you reason out whether you start at 0 and go up and settle to a value, or you start high and go low. For the current, right, we talked about how the current through your inductor, it's going to, at the very beginning when you first connect this, try to maintain the 0. So it's going to start low and then eventually settle to some kind of max value. Whereas the voltage, at the very beginning, at least the magnitude of it, we won't talk about the sign because that's just a direction thing. And start with some initial big voltage, and then as the system reaches equilibrium and this change goes away, you're going to crash out to 0. So the functional form be like that. And then that is, oh, let's call that V max. And then for the voltage, it's just a simple decaying exponential. And then the only new thing here is that your tau is L over R and not R times C. So that was the energizing case, right? This is the energizing. So if you're de-energizing, then you're just left with an inductor and a resistor. And what's not drawn on this picture is that, or I guess I'll make it a little more explicit, is that at the moment you disconnect the battery, there is still some current going through that inductor, which is the current that it is going to maintain for a split second of time. And then over time, as you de-energize and spend the magnetic energy through the resistor, your current will slowly drop down, right? And then the biggest change of the current is going to happen at the beginning, so then that's going to drop down. So for the de-energizing case, we would just have decaying exponential for both voltage and current, again with the same tau. Very similar to your RC circuit. I keep saying that. Doing these kind of problems is basically a matter of finding out the tau and then knowing which equation to use, whether we're talking about energizing, de-energizing, current, or voltage, whichever. Then the next logical step to this whole thing, you might ask, what happens if we put an inductor in a circuit with a capacitor? And that's called RLC circuits. No surprise. Show you the simulation here then. Like that. So I'm going to, so here's a capacitor. Here's an inductor. I'm just going to charge up with a battery right now. Boom. You get a little bit of fire because there's no resistance in that loop. Anyway, what we have is we have one plate charged up positive, the other plate charged up negative. And these little blue balls here around the circuit, it's representing electrons. So even though the current goes from the positive counterclockwise to the negative plate, you're going to see the balls go towards the clockwise direction. So I'm going to close the switch and open that switch. So now we just have a capacitor that has some charge in the circuit with an inductor that is not energized at all because the current was 0. So as it begins, you're going to see that the electrons, because of the charged plate, would want to go clockwise. But when the capacitor becomes totally discharged and stops pushing things clockwise, what's happening is that the inductor now has a current through it. So it wants to maintain that current in the same direction. So it continues pushing the current in the clockwise direction, putting some negative charges onto the other plate until it gets built up enough that the current stops and we go back the other way. And this time we go back, it's going to overshoot again because of the inductor trying to keep it going. And then just go back and forth like that. If I put a ammeter, you'll see that it kind of goes up and down, and then the direction changes. So to actually see the direction, let's put a graph here, and you'll see that the current, in fact, swings back and forth in a sinusoidal pattern. And similarly, the charge across the capacitor, as can be measured by the potential difference across the plates, or the voltage, is also sinusoidal. And in fact, this is why people often call this LC circuit as an LC oscillator, because you can see that the current and the voltage both oscillate sinusoidally, and that you can see that the energy is kind of sloshing back and forth between stored up in the electric field in the capacitor and stored up in the magnetic field in the inductor. And if I write out the loop equation, you might be reminded of an oscillator, of a harmonic oscillator or simple harmonic motion that you would have dealt with in 1125. So this oscillator kind of swings the energy between electric field and magnetic field. So C, this L. So if you do the loop equation, you can think of the capacitor as supplying some kind of voltage, Q over C, minus di dt is equal to 0. That's the loop. But your I is equal to dq dt, so di dt is in fact the second derivative of Q. And now we have a linear second order differential equation. And it's of the exact same form, really, as the simple harmonic motion that you would have seen. So here what we're looking for is a function that looks more or less like itself as its second derivative. In fact, the negative of that. So it's no surprise that the solution we're looking for ends up being some sinusoidal function. There's like phase constant and things you can add in there for depending on initial condition and whatnot, but the basis of it looks like that. This Q naught here is the amplitude, of course, or Q max, you can think of it. So then VC is just Q over C, so then it's going to have the same form, whereas your current is going to be the derivative of the sine, so it becomes cosine. But the most important thing of this whole thing is, of course, what the heck is omega? And omega is equal to 1 over the square root of L times C. No surprise, right? The bigger either of these values are, the longer it will take to either charge it up or to energize it up, meaning it will oscillate slower, has a lower oscillation frequency. And given that, then all the things you kind of learn about a harmonic oscillator from last term really applies to this oscillator as well. Right? All that math for a different system, we just have a different omega. In this case, this is the omega for the LC oscillator. And in theory, this would just slosh up back and forth forever because there's nothing taking the energy away from the system. Which brings us to the next logical step, I guess. The next logical conclusion is, what happens if we add a resistor into the mix? Well, we'll call that an LRC circuit, right? So if we make a resistor, put a resistor in there. This, if you recall from 1125, we briefly talked about damped oscillation, right? There's some friction or some viscosity in the system removing the energy from the from our system. And then so this is kind of doing the same thing, right? The resistance is going to dissipate some of that electrical energy and turn it into thermal energy. So qualitatively, we won't go through all the math, but qualitatively speaking, you still have a current that's going to oscillate back and forth, right, over time. But the amplitude of which is going to decay exponentially. And the oscillation amplitude gets smaller and smaller over time. So that's the extent I need you to know about our LRC circuits. Next, and last but not least, I guess, because it is the last topic we cover, is transformers. It also works off of magnetic induction, so that's why it's included here. And of course, we're not talking about that cool looking transformer. Most real life transformer looks more like this. Quite a bit more boxier. But they are very common. In fact, inside, that's just the outer casing. But what it actually looks like as a transformer, it looks kind of like this. They really are just kind of like a metal casing with some coils of wires inside them. And you'll find one of these in most electronic device around your home. Your computer, if it's not a laptop, would probably have one. In the power supply, most TVs would have one, and that makes up actually most of the weight of these kind of devices. Because big hunk of copper. So what it does is a transformer converts voltages to different values. But, very critically, it only works because the working principle is magnetic induction, right? So you really need this thing to change all the time, to continue to have a change. You need a change in flux to get that induction to happen. So you need a voltage that changes all the time. So that's why most of the time transformer works with an AC voltage. AC meaning alternating current, which is a sinusoidal kind of thing, right? It's possible to build DC transformer, but they're way more complicated and that's really not worth the effort. So in most cases, that's one of the driving reasons why our power generation is done in AC and then therefore transmit in AC, because we can easily what we call step up and step down the voltage of the electricity we're dealing with. So you need that change. So how does it actually work? The inside of a transformer looks like this. There's two kind of separate circuits. One side we call the primary. And that's just the name for the side that's connected to the power input or the energy input, as you can think of it. The squiggly line with a circle, that's our symbol for a voltage source, that's AC. And then the other loop we call secondary. Not that it's any less important, it's just kind of the output, right? Another word for this is input and output. And of course, you can just take the transformer and flop it the other way and it'll do the opposite thing. So there's nothing necessarily special about primary and secondary other than what we hook onto those ends. So how does this all work then? Well, because it's an AC voltage, you have a constant change in the voltage, which means you have a constant change in the current. So then this current will create some magnetic field, which is also constantly changing. And this magnetic field gets channeled, right? We talked about these metal material channels the magnetic field. So now you have a magnetic field that changes within this loop. So now you have a changing magnetic flux, which then gives you some kind of induced EMF or voltage, which then goes to power your resisting your load or whatever device you have. But because the amount of EMF or voltage you get directly depends on the number of loops you have, the voltage here is related as such. It depends on the number of loops in the two coils in a very directly proportional ratio relationship. Super dead simple. And we put these absolute value signs to signify that these are the amplitude of my voltage, because my voltage is going to be changing all the time, right? It's a sinusoid, right? But we can talk about the amplitude of this oscillation. And if you attend my AC lecture, oftentimes people, instead of using amplitude, we use the RMS, root mean square value. And I can tell you all about what that means if you come join us for that lecture instead. And one last thing, energy and therefore power is still conserved. Energy just doesn't disappear into nowhere. And for a ideal transformer, and in fact, most transformer has very little losses. You get some losses just in the heating up of this metal frame here. But for the most part, the power supply by the primary side and the power picked up by the secondary side would be equal. So that's a way to, based on this and combine together, you can relate the currents as well. So when you're not actually magically making more anything, right? If you step up the voltage, you have to end up stepping down the current to have the same power in the end. And that's transformer. Super easy. That's why we include it here. And I think that would be the course. So if you have any question, please feel free to add that to the chat. And thank you for your attention. And I hope these live stream has been helpful despite all the difficulties and transition we've been having. And otherwise, I will continue to post things up on Brightspace, such as your quizzes and practice final and solutions and things like that. And I wish you all the best for your final. And if you would join us for the live streams after the final, that would be really awesome as well. Thank you so much. Yes, unless I'm told otherwise, it'll be very similar to how I did midterm 2, except that I think this time you guys only will get 3 hours, just because you now know how to upload things. The length of it will be similar as all the practice final and all the other tests we've done, 5 multiple choice and 8 longer questions. So really a 2-hour exam, and you get 3 hours to do it as well as to scan it in and submit it. Well, you're all very welcome, and the fun doesn't have to stop there. I keep saying everything we've been doing is building up towards these Maxwell's equation, and it's actually quite neat to see them all come together. So I really hope you join me for that extra thing. But seeing no further question, I'll sign off here. If you have anything, please do reach out to me by email. So thanks again. See you around.